So for this question, we're asked to draw the free body diagram of the jib crane AB, which is pin connected at A and supported by member or link BC. We're then asked to calculate the force in BC and the reactions at A, and these of course are going to come from the diagram. So to start off with, we're only asked to draw the free body diagram of AB, so we can separate out just that component. So for its free body diagram, it's going to look like this. So we can apply the external forces. So first of all, we know it's going to have this 8 kilonewtons pulling it down. Okay. We also know that there's going to be a force acting through this BC member, which is going to hold up our little beam here. Now, looking at this, you should be able to tell that it's a two-force member. Okay, that's because two-force members only have a force on either end. Basically, they're pin connected to other things. So this one has a pin at B and a pin at C, and that's going to mean that the force through this bar can only be in pure tension or pure compression. Now, there's a separate video discussing two-force members if you want to have a look in more detail, but basically what we can say is if this is going to be a two-force member, the force in the bar is going to be in the direction of the bar itself. So if I assume that it's going to be in tension or being held up this way, I'm going to say that the force is FBC, and whatever angle I have for the bar, I'm going to apply it for this force as well. So it's like a little 3, 4, 5 triangle that we need to have. And I've got the 3, 4 and the 5 the wrong way around. Let's just fix that up. So it's 3, 4, 5. Alright, so the other forces that we're going to have are due to the pin connection at A, and because it's a pin, they're going to be able to support a horizontal and a vertical component. Okay, so looking at this, I'm going to assume that since the horizontal component of this force is to the left, my reaction is going to be to the right. And for the vertical part, this is down and this is up, so it's a little hard to tell. I'm going to take a stab and say it is going, I don't know, upwards. Call it AY. Alright, so now we just need to go through and solve for these reactions, which is the second part of the question. So you can be a little bit strategic in how you apply your equilibrium equations. Remember, you have sum of forces in X, sum of forces in Y, and sum of moments at any point have to be equal to 0. So one trick would be if I sum my moments at point A here, both AX and AY are acting through that point, so they're not going to create a moment. And the only unknown that should enter the equation is this FBC, so we can directly solve for it. So let's start with that. And I'm going to treat anti-clockwise as the positive direction. So as we said, neither of these is going to enter the equation. So we now just need to look at the 8 kilonewton force. The distance from its line of action back to point A, we can get from this diagram. It's going to be the 3 meters. And it's going to cause a clockwise rotation about point A, so it's going to be negative. Alright, we now need to separate out FBC into X and Y components, since we're given X and Y distances with respect to A. So if we start with the horizontal component, it's going to be FBC multiplied by the horizontal side divided by the hypotenuse from the triangle, so 4 and 5. Remember that if you're more comfortable, you can always solve for one of the angles inside this triangle and then treat it like normal, knowing the angle in degrees. So this represents the horizontal part of FBC. We just need to multiply by the distance back to point A. So the horizontal force in here acts along this line of action, so the distance becomes 0.4 meters. And the direction, it's going this way about point A, so it's going to be anti-clockwise, which makes it positive. So now for the vertical part, so it's going to be FBC multiplied by the vertical side of the triangle on the hypotenuse, so 3 on 5. We then need to multiply by the distance, so we're looking at the vertical part, which has a line of action up and down here. So the distance back to point A is going to be 7 meters, and it's going to try and push us anti-clockwise about point A. Okay, so it's going to be positive. So this is equal to 0, and we've only got one unknown in the equation as expected, so it's just a matter of solving for it. So if you put together all these things with FBC in them, you end up with 4.52 times FBC, and if you swing the constant to the other side of the equation, it becomes positive 24. So FBC is equal to this divided by this, which is 5.31 kilonewtons. So it's come out positive. That means it's in the correct direction on this diagram, so it's going to be like that. If it had come out negative, we just would have needed to swap the end that the arrow was on over. Alright, so now we have two more unknowns that we need to find. Again, you have options on which order you apply your equilibrium equations and which ones you actually go about applying. I think I'm just going to go with sum of forces in X and then sum of forces in Y. It doesn't matter too much at this stage because you should end up with only one unknown in each of those equations. So if we sum in the X direction, we're going to have positive AX. Neither of these has an X component. We're going to have X component from this one. It's going backwards, so it's going to be negative, and it's going to be 5.31. So we're looking for the X component, which means we take the X side of the triangle and divide by the hypotenuse, so it's going to be 4 divided by 5. So AX works out to be 4.25. And the units are going to be kilonewtons. And it comes out as a positive value. That means it's in the correct direction on the diagram, so it is to the right. And finally, we just need the AY variable, and we can get that probably most easily by summing in the Y direction. So we have AY going up, 8 going down, and some component of this going up. It's going to be 5.31. Looking for the vertical part, so it's going to be the vertical side divided by the hypotenuse, which is 3 on 5. And rearranging to get AY on its own, it comes out to be 4.81 kilonewtons. Again, it comes out positive, which tells us that the direction was correct over here, so it is going upwards. So these are the three answers that we were looking for in order to answer the question. That's all there is. See you in the next video.